This is the last lecture of Chapter 3 for functional groups. But before we actually get into the material, let's just do a quick review of what we did in the last lecture. We looked at the nomenclature of alcohols. We also looked at the classifications of alcohols, such as primary, secondary, and tertiary alcohols. Next, we looked at aldehydes and the nomenclature of aldehydes. Make sure you identify the functional group of the aldehyde. It has an H that's bonded to the carbonyl carbon. And we looked at ketones and the nomenclature of ketones. So those are what we've covered already. In this lecture, we will look at a few more functional groups in terms of IUPAC naming, and then we'll conclude with infrared spectroscopy. So for today, what we'll look at is carboxylic acids and the nomenclature. Esters, another functional group, and the nomenclature. Acid chlorides, and amines, and amides, and lastly we'll look at infrared spectroscopy. This is a technique that's used to determine the functional groups that are present in unknown molecules. But we'll say more later on. Okay, let us start. So here we'll look at carboxylic acids and the nomenclature. But first of all, let's make sure we can identify carboxylic acids. Here is the functional group. Notice it's the entire carbonyl group, carbon oxygen double bond, and the O and H. So it's not really a ketone and an alcohol. So make sure that you look at this in detail. Remember, we defined a functional group as a region of the molecule where there is a specific arrangement of heteroatoms. A specific arrangement. So here's that specific arrangement for carboxylic acids. Sometimes you'll see it written like this, where the OH is just written as OH. Sometimes you'll see it written as this, COOH, but you should know we are really making reference to that structure. Also, you'll see it written as this, RCO2H. Bear in mind, this is the functional group right here, and that's a carboxylic acid. Let us look here at some common ones that we are familiar with. Here's one that's used in the treatment of arthritis. Here is a functional group, carboxylic acid, naproxen. Ibuprofen, it is a carboxylic acid. Granted, now we know it is aromatic, or benzene ring is also present. Acetic acid, found in vinegar and salad dressing. Here is the carboxylic acid functionality. And aspirin, it's a carboxylic acid, and here it is. Here's another functional group though that we look at today in terms of the nomenclature. So it's an ester and also a carboxylic acid and a benzene ring. Okay, let us turn our attention now into the actual IUPAC nomenclature. So here are examples of carboxylic acids. And here's the carboxylic acid right here. Here's the carbon of the carboxylic acid though. That's important because that is the carbon that we'll use in terms of the numbering. So the correct numbering is to start at this carbon and find the longest chain. So as you can expect, this is not a correct numbering because the carboxylic acid group now takes priority over all the groups that we have done so far. The alkenes, the alkynes, and the alcohols. So this would be the correct numbering system. 5 carbons. The root name for that 5 carbons would be pentane. So it now becomes a modification on that pentane. So let's see how we modify that name to get a carboxylic acid. For the alkane, you change the E to oic and add the word acid. So the final name is an alkanoic acid. One thing I should point out here though, based on what we've seen before, here's an A. So right away, you know that if you have an unsaturated carboxylic acid, that A can be changed to an E to indicate the presence of unsaturation, but we'll get there. So in terms of naming this carboxylic acid here, this is number 1, and it has 5 carbons, so it becomes pentanoic and the word acid. Pentanoic acid. Here is another example here, 6 carbons, hexanoic acid. Notice we need not put 1 to indicate the presence of the acid because it is a terminal functional group. Just like your aldehyde, it has to be at the end of the molecule or starting point in numbering. A couple more examples here. We'll just quickly go through this. Here's a carbon of interest. Identify that carbon and you go the longest chain. So that's 5 carbons. So it becomes a pentanoic acid on carbons number 3, and then carbons number 4. Carbon number 4, they are methyl groups. So it becomes 3 comma 4 hyphen. Don't forget the dimethyl. It's a dimethyl. Don't forget that because we do take off points if the name is not exact. Because remember, this is a communication of the names and structure. So we have to get that correct in terms of a systematic naming. Here's another example. Here's the carboxylic acid right here. Here is the carbon of the carboxylic acid. The longest chain again is here, 5 carbons. So it's pentanoic acid because of this functional group on carbons 2 and then carbon 3 is a substituent. Let's put it this way. On carbon 2 and 3 are substituents. So we have to name this. This is an ethyl group and a methyl group. So E comes before M, so it's a 2-methyl and a 2-ethyl, pardon me, and a 3-methyl pentanoic acid. Let's look at, as we said earlier, unsaturated carboxylic acid. So here's the unsaturation right here. And let's see how we're going to name this. So in other words, we do not start from the end closest to the double bond because that's now of lowest priority compared to the carboxylic acid functionality. So this carbon is number 1. So identify your functional groups on the molecule, determine which has the highest priority, and name it based on that highest priority functionality that's present. So this is number 1, and the longest chain here would be 5. So it's going to be a pentanoic acid right here. However, we have unsaturation here on carbon 2. It starts at carbon 2. So here's that E to represent the unsaturation and the number 2 to indicate the presence of the ene and of course our methyl. Again, I hope you can manage this because you will be applying this to different systems. If you had a triple bond in the molecule, you can imagine this goes to a Y because that's the alkyne, and the same systematic way is you describe the position of that alkyne by a number. So expect molecules like that. Okay, let us look at another functionality here, and this is esters. Notice it's esters of carboxylic acids. Why? Because you'll notice here from the functional group, it looks pretty much like a carboxylic acid, except this H from the carboxylic acid is now an alkyl group or carbon containing group. So look out for that. It looks pretty close to a carboxylic acid, but it's not, because this is an R group. So it can be written like this or written like this. Notice the ester group is right here, or like this, or a lot of times it's written like RCO2R. These are all representations of the ester functionality. Let us look at some common esters. By the way, they are typically sweet-smelling compounds, the characteristic odor. So they're used a lot in perfumes and in flavorings. So here's one. This one is isoamyl acetate. Well, that's a common name, and it's in banana. Whenever it's done in the lab, the entire floor smells like banana. Another one is orange. This is right here, but notice the ester functionality is right here. And another one here is pineapple, and here's the ester functionality. So these molecules differ from each other based on the R group that are here. So this is a methyl, but this group here is different from this group. So that makes it, gives it a different molecule and hence different in properties. Let us now look at how we name these molecules. They're named as alkyl alkanoates. Keyword here is alkanoate. So identify your functional group here, the ester. This group here, this alkyl group, goes first. And this part here goes last, but it's changed to an alkanoate, O8, based on the number of carbons that are in this portion of the molecule. So let's look at an example here. So here's our functional group right here, but this carbon is a carbon of the O8, 2 carbons, so it's an ethanoate. This oxygen contains the alkyl group, and it has 1, 2, 3 carbons, so it's a propyl. So we name it as a propyl ethanoate. Notice ethanoate because it has 2 carbons over here. So again, you should be able to recognize the ester functionality, recognize the alkyl group that's bonded to the oxygen, name that first, and then the other portion is named as an alkanoate. Here's some examples. So here's the ester right here. Here's the alkyl group that's bonded to the ester, 1, 2, 3. So that's a propyl. That comes first. Here's the other portion of the molecule known as the alkanoate. This is carbon number 1. So 1, 2, 3, 4, 5, and 6. Hexane, but we changed that to an O8. We changed the E of the alkane to O8, so it becomes propyl hexanoate. 2 words, propyl hexanoate. If you have substituents on these groups, you just follow the systematic way we had before. So here again is our ester. Here is the alkyl group. It's a 1, 2, 3, but on the second carbon is a methyl group, so it becomes 2-methyl propyl, the first part, and this part here is a 1, 2, 3, 4, 5, 6 hexanoate, but on carbons 3 and 4 is a dimethyl, so it becomes 3,4-dimethyl hexanoate. Okay, so once again, you need to practice naming this, but you first have to recognize the functional group, the structure, and the groups that are bonded to it, and name it accordingly. Okay, let's look at another aspect here of esters. Now we're looking at cyclic esters. As you can imagine, esters can be in the form of a ring. So it's not a terminal functional group, it is one that's interior. So here we go. So here is a ring, and here is the ester functionality. But if it's in the form of a ring, it's usually described as lactones. So you'll see that name quite a bit. Lactones are really cyclic esters. So again, of course, as you know, in chemistry, we have these terms that we use to communicate. So you have to have a good understanding of these terms when we write them in quizzes and in exams. So lactone is a cyclic ester. How do we name it? We first have to recognize the ester group here. But in terms of naming it, we recognize this as the carbonyl portion, and we name that as an one, just like the ketones. But there is an oxygen here, and we name that as an oxa. In terms of numbering, this always gets number 1 because that's priority, and we go in the direction of the oxygen, so it becomes 2-oxa because that's on carbon number 2, oxa. So this oxa here goes here, and the 2 is to show that position of the oxa. And of course it's a cycloalkanone. Alkanone here, looks like that spelling is a little off, C-Y-C-L-O. But that's a cycloalkanone here, where the number of atoms in that ring will in fact tell you the exact name. Some examples. So here's one. And this is, here's the ester right here. Here is number 1. So that will be our alkanone portion. Here is number 2. This will be our oxa. So it's always 2-oxa. Notice that, always 2, because you're going in the direction of the oxygen. Since we have 6 atoms in this ring, it's a cyclohexanone. So the full name is 2-oxa cyclohexanone. As you can imagine, once you have the numbering system here, if there are substituents on these carbons, you just have to describe the type substituent and a number to describe its location. And here are some examples for that. So here's a carbonyl. Here's the carbonyl of the ester. Here's the oxygen, the oxa of the ester. It's a 5-membered ring, and here is an ethyl group, pardon me. So it's a cyclopentanone and 2-oxa, and we have an ethyl group on number 4. So this is 1, 2, 3, and 4. Same here. So once again, you should be able to go from name to structure. So when you're reviewing, just write this name on a piece of paper, on a sheet of paper, and see if you can come up with the actual structure based on the name. Because as I mentioned on the quiz and on the test, we'll go from name for you to give us the structure. We'll give you the structure for you to give us the name. So make sure you can go on either way in terms of naming these molecules. Next, we look at another functional group called the acid chlorides. Here is the acid chloride functional group. Notice this has a Cl in this position bonded to the carbon of the carbon-oxygen double bond. So we have here one example. Here's a chloride and here's a carbonyl. And of course, these are different. Acid chlorides are very reactive molecules. We'll use them quite a bit later on in the course when we're looking at synthesis of some larger molecules. If you should open a bottle of acid chloride in the lab, it's called a lacrimator because it will irritate your eyes and your skin because it reacts readily with moisture. And see, but we'll get more into reactions later on. Let us look now at the nomenclature. So I hope you're seeing a systematic way here, and that's why the IUPAC is a systematic method of naming organic molecules. So hopefully you've seen a systematic way here. So in naming acid chlorides, we change the E of the alkane to oil, OYL, and we add the word chloride. So the full name becomes alkanoyl chloride. Notice again this A here. So if we have an unsaturated alkanoyl chloride, we can change that A to an E and indicate the position of the double bond if it's a double bond, or that A to a Y if it's a triple bond, and indicate the position of the triple bond. But we'll get to that later on. So in naming acid chloride, of course now we know this carbon is a carbon of importance in naming. So we start here by giving this number 1, and we find the longest chain. The longest chain here has 5 carbons, so we know it's going to be pentane as a starting point. We change the E to oil, and we add the word chloride, so the name becomes pentanoyl chloride. Here's another one. 6 carbons, hexanoyl chloride. Let us look at branched acid chloride. Again, we'll just do one because I'm pretty sure you're getting the systematic way of doing it here. So recognize, of course, the acid chloride, which is right here. Carbon of importance in terms of naming and numbering is right here. Longest chain, 5 carbons. So it becomes a pentanoyl chloride. Why oil chloride? Because of this group right here. And we have on carbons 3 and 4 substituents. It happens to be a methyl group here and a methyl group here. So it becomes a dimethyl, and they are on carbons 3 and 4. Again, make sure you include your comma for separating numbers, and make sure you include your hyphen or a dash for separating numbers from letters. So again, you may want to just write this name on a sheet of paper and see if you can come up with that as your structure. As we said earlier, no surprise here. If you have a double bond or an unsaturation in your acid chloride, you have a systematic way of doing it. You just change the A to an E as shown here and indicate its position. So we go 1, this carbon is a starting point, and it has 5 carbons, so it's a pentanoyl chloride. It has a double bond, so we change that A to an E and indicate the position of that E using this number 2. On carbon number 4 is a methyl group, so it becomes a 4-methyl 2-pentenoyl chloride. Okay, let's turn our attention now to amines. Okay, so again, there are a lot of amines that we will be working with in this course, and a lot of amines that exists in nature. So as scientists, whenever you have a lot of information to deal with, the best way of dealing with that lot of information is to put them into categories, into little baskets, and we study those that are similar. So in terms of similarities, we have here ammonia, where there is a nitrogen, and we have 3 hydrogens bonded to nitrogen. Of course, there's only one possibility there, so that's why that's called ammonia. But here comes variations. If you have the nitrogen, which indicate the presence of an amine, so notice the amine has the nitrogen, the heteroatom nitrogen. If there's one alkyl group that's bonded, it's called a primary amine. Sometimes you'll see it written as 1 superscript 0. If it has 2 alkyl groups, it's a secondary. And of course, 3 would be a tertiary amine. It's possible to have 4 groups bonded to nitrogen, but then it becomes a cation, a salt, because it has a formal charge of +1, so that becomes a quaternary ammonium salt. It's possible to have nitrogen in the form of a ring that's aromatic, and we'll study that later on, but those are called aromatic amines. But the concentration for the first part of this course will be on primary, secondary, and tertiary amines. Let us look here at some examples. As a matter of fact, these are examples that's been in the news recently, and I hope you guys are following what's happening in the news in terms of chemistry. Here is 3 that's very useful here. We have novocaine. Notice nitrogen and 2 groups bonded to it. Notice again, novocaine has another functionality here. Okay, histamine, here's the nitrogen, and here's the aromatic amine that we talked about earlier. And dopamine has here the nitrogen, and here is the OH, and an aromatic amine, and the benzene ring. But for this portion of the course, this is the amine. Here are 2 amines that's been in the news recently. I got a little ahead of myself there, but here are 2. Chloroquine, in terms of the COVID treatment. One proposed molecule or compound that can treat that is chloroquine, but it has been proven for a drug for malaria. Here it is. So you can see here is the nitrogen, and that's a tertiary amine, isn't it? Because it has 3 alkyl groups. Here's another nitrogen, but that's a secondary amine because it has 1 hydrogen and 2 alkyl groups bonded to that nitrogen. Here's another nitrogen, and that's an aromatic amine. Hydroxychloroquine is another one, another variation of chloroquine. And of course, here's the nitrogen, tertiary amine. Here's another one, and here's another one. The only difference, of course, is the hydroxy group, making it hydroxychloroquine. Let us look at the nomenclature of amines. Again, here is the amine functionality. Here's a carbon that has the amine functionality. So, we'll have to number, find the longest chain that has this group in it. We can start at this end, or we can start at this end. Of course, as you know now from experience, the amine will take priority. So we start at the end closest to the amine. So this becomes the correct starting point here. And we go in this direction, so it has 6 carbons. So this would not be the correct numbering system here. So with that said, let us see if we can apply this here. So the amine is, so you change the A of the alkane to, the E of the alkane to amine. So the name becomes alkanamine. Alkanamine, so the E goes to amine. Notice again that A, which can be changed if you had here an unsaturation. But before we do that, let's get into the basic nomenclature. So let's see if we can name this molecule. Again, we start at this end because it is closest to the amine functionality. So 1, 2, 3, 4, 5, 6. 6 would be hexane as a starting point or the parent. We change the E of the hexane to amine, so it becomes hexanamine. However, we need to indicate where that amine is because it could be on either one of these carbons. It's on carbon number 3. Here's another example. Here it's on carbon number 2. Here it's on carbon number 2, but here it's pentane. So it becomes pentanamine. So you get the idea. So let us look at another type of amine here, and this is putting a group on secondary and tertiary amines. So here we still identify the longest chain that has the amine functionality. But notice, this amine is now secondary, so it has a group bonded to this nitrogen. So we say that it's an N-methyl. So the N here is to indicate that this methyl is bonded to the nitrogen and not on the chain. Same here. N-ethyl. The ethyl group is on the nitrogen and not on the longest chain. And of course, if we have two methyl groups, it would be NN. Don't forget the NN, because two N's would represent two methyls, so it's a it's a dimethyl, and of course you have to indicate the position that this group is on. It's on carbon number 2, so that's why it's a 2-hexanamine. Same here. This is just another way of writing the same molecule. Okay, let us look here at branched amines. As you can see, we start here again. Here's the amine functionality. So you can see the first thing is to recognize the functional group. That's why in the first part of this chapter, we had you, or in the last chapter, we had you recognize functional groups, be able to identify functional groups, because it will become very important in naming. So this is the amine. Start at this end. We have 6 carbons, so it becomes an hexanamine. We have to indicate the position of that amine. It's on carbon number 3. On carbon number 5 is a methyl group, so it's 5-methyl hexanamine. Try this again. Write this on a sheet of paper and see if you can come up with a structure, and then check to see if that's the structure you came up with. Let us look at amides. So amides, here's the functional group of the amide right here. This is an alkyl group that's bonded to this carbon, but this group right here, carbon-oxygen double bond, now it's bonded to a nitrogen. You will notice that the carbon-oxygen double bond is a very common feature in organic chemistry. It's bonded to, if it's bonded to an OH, it's a carboxylic acid. If it's bonded to an OR, it's an ester. If it's bonded to a chlorine, it's an acid chloride. And now we see it bonded to an N. And that specific arrangement is called an amide functional group. Classification. So this is a primary amide because this nitrogen here is bonded to only one alkyl group back here and 2 hydrogens. Secondary because we have 2 alkyl groups here, or 2 groups bonded to this nitrogen, and a tertiary would be 3 groups. So again, you should be able to classify amides as primary, secondary, or tertiary. Here's an example of a dipeptide, and of course, as you know from your biology course, peptides are really amino acids that are joined together by an amide bond. So here's the amide bond right here. And here's one amino acid, and here's another amino acid to make that a dipeptide. Let us look at the nomenclature. So once again, identify the functional group. Notice again we are identifying the carbon of the carbonyl of that functional group. And we start numbering. 1, 2, 3, 4. Or let's go over here. 1, 2, 3, 4, 5. So this is the longest chain. So this now becomes a substituent of that longest chain. So before we even go to the next slide, you should have an idea of how to name this. How do we name the amides? Here's the systematic way. We change the E of the alkane that has the longest chain to amide. So the name becomes alkanamide. Again, notice that A. So this is an alkanamide. So here we go. So this is carbon number 1 of the amide. And we go in this direction, 5 carbons. So it's a pentanamide. On carbon number 4 is a methyl group. On carbon number 2 is an ethyl group. So that's why it's 2-ethyl. E comes before M. 4-methyl pentanamide. Do the same here. So write this on a sheet of paper and see if you can come up with this as the structure. Okay? Using that systematic way of naming these molecules, in this case the amides. Okay, let's turn our attention for a few minutes here to infrared spectroscopy. You may be wondering, what's the relationship between spectroscopy and functional groups? But let's see if we can just introduce this topic here and the relationship. Infrared is, of course, a region of the electromagnetic spectrum, energy in that region. So when molecules are exposed to energy, they're excited. When they're exposed to specific energy in the infrared region of the molecule, they are excited, but in a specific way. Keyword, they are excited in a specific way. The way that they are excited is that the bonds vibrate. The bonds vibrate in a predictable manner. So we got some keywords here. The bonds vibrate and bend in a predictable manner. So in other words, here is a molecule, carbon dioxide. If that should be exposed to infrared radiation, the excitation, which would now be bond vibration and bending, will be in a predictable manner. Predictable means that in a specific region of the infrared spectrum, and notice this is given as reciprocal centimeters. You may remember from your physics course, that's a relationship. There's a relationship between wave number and energy. So this is a specific region of the infrared energy spectrum, and it has a specific and predictable vibration for this bond. It has another predictable type vibration here, a bending at this region, and here's another one. So the bottom line here is that you take a molecule such as carbon dioxide and you expose it to infrared radiation at specific regions of that spectrum, of that range of energy. The molecule will get excited and do specific and predictable excitations, typically bond bending and bond vibration. Now if we take that concept and we put it in form of a spectrum, so let's look at this. This is a spectrum here. So we have here the wave number, which is of course related to energy. So what we're doing is we're buying a very expensive instrument that's called the infrared spectrometer. And what it does is it can produce energy at specific regions of the infrared spectrum, of the electromagnetic spectrum. So at specific regions here, such as 1,000 reciprocal centimeters, 2,000 reciprocal centimeters, 3,000 reciprocal centimeters, it can give energy in that region. So if you take a molecule such as methanol and expose it to infrared radiation at a specific region, right in this region here of that energy, these bonds will start vibrating, and specifically this OH bond here will start vibrating. And the instrument can detect that vibration because the molecules accepted the energy to be excited. So the instrument quickly recognizes that citation and gives a signal. So here is the signal. So the bottom line is, if you have a molecule such as methanol, which has the OH functionality, notice the OH functionality here. So this could be an R group bonded back here. Once it has this group here, OH, we will see in the infrared spectrum a signal, also known as a band, right here at around 35 reciprocal centimeters. So that's one way of telling or giving gaining an idea of the type functional group in a molecule. So you take any alcohol and subject it to the infrared radiation. When the energy gets to this region, 3,500 reciprocal centimeters, we will see a signal because an excitation occurs. Let's look at one last example. Here's another one. This molecule is acetone. But let's pretend we did not know it was acetone. But it has a specific feature here, the carbon-oxygen double bond, ketone. When that molecule that has the carbon-oxygen double bond in the form of a ketone is exposed to energy in the infrared region of the electromagnetic spectrum, at 1710 reciprocal centimeters, we will see a signal. Here is a signal right here, because the molecule will absorb energy and a specific and predictable bond excitation, vibration occurs, and it occurs right here in this region of the electromagnetic spectrum at 1710. Notice that there's no band here. So that means that this molecule did not have an OH functionality. But since it has an excitation here, or a band, or a signal at 1710, it indicates that this molecule had a ketone present. So all molecules, all unknown compounds that have a ketone, we will see a signal at around 1710 in the infrared spectrum. So that's the relationship to functional groups. The next slide here has a summary, and this is the last one. So that means that all the functional groups that we have studied so far, if molecules have any one of these functional groups, and you should put that in an infrared spectrometer, where you scan the region of the infrared radiation, at specific regions, different functional groups will have excitation. It will absorb that energy from the infrared radiation spectrometer, and there will be a signal because the instrument is programmed to recognize when energy is absorbed. So here's just a summary. We'll have a chapter later on next semester, well, this semester actually, when we actually look at a much broader examples of functional groups. So here's a carbon-carbon triple bond. It gets excited at around 33 reciprocal centimeters. We've seen the carbonyls before. They get excited right in this region. The OH we've seen before, right in this region. Notice the NH is in this region. So again, and of course the nitrile is in this region. So once again, if there's an unknown compound, you do not know what functional group is present in that unknown compound, the infrared spectrum or the infrared spectroscopy can be used to determine or give you an idea of what functional group is present. Okay? Okay, this is the last slide, of this lecture, and of course the last lecture of this chapter. So once again, go ahead, read what's in your textbook, and make sure you understand all the concepts. Equally important though, make sure you can apply these concepts to solving problems. So work lots of problems, and of course on the tutorial, make sure you work that. Make sure you don't just work it to get answers. You literally work it. I would anticipate that each student may get a slightly different answer, but again, you need to double check that with each other students, and also double check that with the answer key. But the whole aspect here is that you practice. So keep practice. Okay? So all the best. Continue to study hard. And I'll present another lecture on chapter 4 during this week. So look out for that. So continue to study. Okay?